outside the EUMETSAT building with this stunning pond and satellites in the background. Tell me about your role in this organisation.
So you see EUMETSAT is a sort of ship. You see the sea and I'm the captain of the ship. And what the ship is about is interaction between scientists, engineers and users. This is the melting pot of EUMETSAT.
So when it comes to what the satellites are doing, you're responsible for making sure that this operation works smoothly.
Yes, I think it's complex because we develop new systems, so we prepare the future, but we also operate the current system, and here we need to deliver around the clock products, informations to users, and we need to improve this information with science, new algorithms, and that's what we do on a day-to-day. Controlling the spacecraft is a prerequisite to get information from them, but then a lot remains to be done. Acquire the data, process, validate, calibrate, and also interface with the users to see if they are happy.
So that's a huge amount of work behind the scenes just to get these data.
Yes, absolutely. And if you visit the control room, you see a few people, but behind you have a lot of people working, developing products, information. And then when something is new, everybody comes to put it online, and this is quite exciting for everybody. And this is where the scientists and the engineer work well together.
When we look up at the sky, not so much on a nice sunny day like today, but we look up and we see clouds moving around, and that's what we think of as weather. But the ocean is also dynamic, it's moving
Yes,
around.
absolutely. And if you look at history, we did not know much about the dynamics of the ocean. For instance, the World Ocean Circulation Experiment was just about knowing about the average of the currents, etc. But now, and this is thanks to satellites, we are developing operational oceanography, forecasting the ocean in 3 dimensions, in 4 dimensions. And this is quite new. Meteorologists were almost convinced it was as simple as the atmosphere, but it was very, very different because the scales are much smaller. You know, when you have a storm with a diameter of 1,500 kilometers, the equivalent in the ocean is an eddy which is 20 kilometers large. So you need sampling, much more observation, and the only way is satellites, because you cannot have a buoy every 10 kilometers.
Tell me about the Copernicus system briefly.
Copernicus is a large program addressing a lot of topics. We are focusing on atmosphere and ocean in EUMETSAT. We have delegation to operate the Sentinel mission, which monitor the atmosphere and the ocean. And Sentinel-3 is the main one, but Jason-3 is also a Copernicus mission. Sometimes it's forgotten. For us, we are also contributing to Copernicus with our own mission, because the main objective for us is to achieve the best possible synergy, not for us, but for the users, between the Copernicus dedicated mission, so Sentinel-3 and Jason-3, and our own mission, METEOSAT, because there are a lot of ocean parameters which we can retrieve for our own mission. For instance, sea surface temperature, but also with METEOSAT, we measure the solar energy which is available to the ocean, which is only available from the geostationary orbit. And we also observe winds, ocean-surface winds, from the METOP satellites with the radar. So all the challenge is to make this data stream available to the users, and they will use everything. If you take, for instance, the offshore industry, they are interested in marine meteorology, they need to know about the winds, but also in the currents.
So this takes a long time, you know, the development of these satellites, it's a very careful process, isn't it?
It's a careful and difficult process because, of course, you think about the satellite, but you need to integrate the satellite with the ground segment to test everything, because when you're in orbit, it's too late. You don't repair a satellite, so you need to be fully ready. So it requires a lot of preparedness, reviews, testing, validation, rehearsal, and that's something which is not in people's mind, but it's terribly important to have efficient and operational systems.
But it's important, isn't it? Even though it's difficult, looking at the ocean using satellites is an important thing to do.
Yes, because the ocean is terribly important. First of all, you know, everybody knows it's 70% of the surface of the globe, but if you look at climate, it uptakes 50% of our CO2 and also most of the heat. So it's clearly the moderator of the climate and the climate change. So we need to understand, if you don't understand the ocean, you have no chance to understand climate, and the more so for climate change. But if you look also at heat waves today, it has to do with the ocean, because the ocean is the memory of the Earth system. So when the ocean is warm, it remains warm because there is a lot of thermal inertia in the ocean, and it influences the atmosphere on the long run for weeks, months and days. And you have also El Niño. So you see, the ocean is a very important element from the planet, and as I told you, it's very difficult to observe, not only because of the scales that you need to resolve, but also because the ocean is opaque. So in the atmosphere, you can do sounding from space, from ground, but in the ocean, it's very difficult. You can do it with floats, not very frequently. So satellites are very important, but it's a challenge because you observe the surface and you need to infer information in the depth of the ocean from what you get from the surface. And this is where the modeling comes into the picture. And this is a big challenge, but it works. And the next challenge will be what we call the bio-ocean, because we have ocean color, we have the carbon cycle in the ocean, we start to have observations from space, we can mix them with the dynamics of the ocean, and then we can even think of looking at the climate of the ocean, which is extremely important for fish stocks, for instance. We see the ocean as influencing the climate, but the ocean will have its own climate.
So tell me about what's coming online.
This summer we have 2 new birds in orbit, so you know Jason 3 and Sentinel-3, and these are ocean satellites. So since 1st of July, the Jason 3 data is flowing to the users. It means that after a few months of calibration, commissioning, we found out, and the scientists found out, the data is good enough to go to the users. We have still the most accurate products to validate, and this will happen in November. So that's for Jason 3. And for Sentinel-3, it's very recent. We took over the satellite operations from ESA, and now we will ramp up the production of products and again deliver data very soon. So it means we have 2 ocean satellites going together, which is quite unique.
So everything that we are doing by launching satellite and observing our planet is really in support of many policies. Today we are mostly speaking about marine area, but it's true that all the other services look in the land management, in the emergency situation in support of civil protection. Another point that is quite important is the border surveillance. We are looking also into aspects of climate change. So really a lot of policies that are very important.
For centuries, humans have looked at the ocean and we've touched it and floated on it. And now we're starting to look at it using satellites from a long way away. Tell me about how satellites are contributing to our picture of the oceans.
Well, let's say 20 or 25 years ago, we tried using satellites for what they do very well, is to monitor the surface of the ocean very quickly and to provide us with a beautiful picture of what is the surface of the ocean. Quickly means in 10 days, for instance, they can cover everything. It took 1 century with different sea campaigns to have this kind of maps. So we had something which was impressive for us, for oceanographers. And then start the second part, which is to go into this 3D dimension, to ingest all this data, this satellite data, into what we call a model, which is a cube, a 3D cube of the ocean. We ingest the satellite data on the surface. We put what we have in situ, the buoys and the drifting buoys, etc. And then we are able to translate this satellite and buoys information into a completely consistent depiction of the ocean with the currents, with the ice, with the acidity, with the salinity, consistent in space and time. And then we push the model forward and we have a forecast for the coming days and weeks.
How close are you to the ideal ocean model now? How far along the journey are we?
So what I was explaining is true. This is what we do every day. So this is really the situation. We are forecasting the ocean every day, thanks to the satellite data, thanks to the collaboration we have with EUMETSAT, with all this data, with the in-situ data we have in real time, and we forecast the ocean. How accurate it is? Well, we go at sea, or people going at sea, the scientists, with the research campaigns, and they compare what we forecast and what they have. And it's not so bad. And the proof of it is that 50% of our users are scientists, so they trust what we forecast. And so there is this mix of real oceanographers going at sea, observing the oceans, and these digital oceanographers that are simulating the ocean. And these 2 communities are getting along very well. We are the same community, which is the beauty of this operational oceanography.